Good evening, guys. Am I audible? Am I audible?
Yes, sir.
Yes, sir.
Okay. So, can we get started? Just give me a second.
Yes, sir.
Just give me a second. Yeah. Today, we'll be starting the last chapter of your 12th standard, that is Semiconductor Electronics, Materials, Devices, and Simple Circuits based on it. Okay. So, till now, we would have discussed about conductors. Right? We would have discussed about conductor. So, we know that conductors are materials which conduct electricity. Correct? So, what is the counterpart of conductor? Obviously, it's an insulator or a non-conductor. The more technical name is insulator. Insulator is that material which doesn't conduct electricity. Then, what is this semiconductor all about? Can someone tell me? Can you tell me what does this chapter mainly deal with?
Sir, semiconductor is a device which has conducting properties intermediate to that of an insulator and a good conductor.
Very good. Very good. So as the name suggests, semiconductor, semi is something in between, right? So semiconductors exhibit the property that is shown. So it exhibits an intermediate property of a conductor and an insulator, like how you told. Now let's come to another point. I'm using the word semiconductor electronics, right? So what is this electronics all about? So semiconductors are devices. What is this electronics we are trying to talk about? What is this? Any idea? So we have studied electricals, right? There are two different things. One is electrical and electronics, which sound similar, but they are not the same. Okay. So I just want to hear from your mouth on what is your understanding of the difference between electric and electronics. Even if it is wrong, it is fine. Let's have a discussion. So what do you think is the difference between electrical and electronic? At least you can give me the name of the chapter which deals mainly about electricals, or we are mainly concerned about electrical engineering. You can either tell me the chapter name from your 12th standard or a real-time example, whichever you are convenient in your thought processes. Please let me know. Can you try?
Sorry, electronics means like is the deals with electrons, sir. Electrical means it like says what's the power of electrons or like state of electrons it says. Electronics means the flow of electrons like that.
Okay, correct. So you're almost there. Electronics is a branch of physics where you're concerned about how the flow of electrons is going to be. But yeah, electrical is also, these both fall under a branch of physics. Rather, I can say on a wider group, they fall under a branch of engineering, where in electrical, you will be dealing with more of components which are bigger in size. See, for example, your fan is there, right? You have fan at your home. So that fan is what actually? Is it an electrical device or an electronic device? Your fan, which is revolving, is it an electrical device or an electronic device? Think about it.
Electrical.
Electronic.
Electrical, sir.
Electrical.
It is an electrical device.
Converts the energy, sir.
Okay. Where it converts from one form to another, accepted. Then what are all the examples of electronics? Then? What are all the electronic devices which you know in real time?
Your phone.
Exactly. So you talk about your mobile phone, tablets.
Capacitors.
Capacitor is not it's not, I cannot call it as an electronic or electrical device because it is used in both. See, for example, since you told capacitor, I'm not sure if you have seen this. This is how a capacitor looks like. So this is a capacitor, this is a capacitor, 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 capacitor. Okay. So it falls under both because we use in both the cases. I'm not sure. Have you ever observed, let's say, if you have observed, please let me know about this. Okay. Have you ever observed when your fan is not working, the person who's coming to repair it will check something like there'll be a device like this. There'll be a device like a cylinder with a wire like this. They'll generally say the condenser is gone. First thing that they'll check is this. Have you ever heard the word called as condenser not working for a fan? If yes, please tell me yes or else no. So you're not sure of it, right? That's what I understand. So next time observe it, okay? They say the condenser doesn't work. So this condenser is nothing but a common name for a capacitor. Condenser is basically a capacitor. So what I'm trying to say is the capacitor is used even in electrical device as well as your mobile phones and all those things also. Okay, so this is how the branches are basically classified. And if you see, this is not what we are going to majorly discuss here. Okay, the semiconductor electronics, for those who are planning to take electronics and communication engineering or electronics and instrumentation engineering or electronics and electrical engineering. So wherever electronics you are planning to take in your engineering, right? This chapter will be one of the bases of which we'll be discussing the most basic things. I just gave this introduction for you to have an understanding of where it is applicable in real life. Okay. So shall we get started with the topics? So the topics that are getting covered in this chapter are, first we are going to see what is the introduction of this chapter, then we'll get into the classification of metals, conductors and semiconductors. Then we'll be seeing about two types of semiconductors which are called as intrinsic and extrinsic. Then we'll be discussing about a device or a diode called as PN junction diode. Then we'll be discussing about the different types of diodes. Okay. That is a special purpose PN junction diodes is what we are going to discuss. With that, it is over. Actually, you have two more topics also, transistors and logic gates. But the transistor and logic gate is removed from your syllabus. So we are not going to discuss about it. If we have to get started, let's see what is the introduction of this chapter. We will go as per the requirement of the exam. I'll go from the exam point of view. Wherever I need to give you real life examples, that time I'll touch on. Okay. So semiconductors. Basically, you would have observed that there are certain materials like germanium and silicon which have this resistivity which is falling between good conductors like copper and insulators like glass. So these kind of materials are what are called as semiconductors. Okay, so if you talk about a material which has resistivity between that of a conductor and insulator is what is known as a semiconductor. And generally, if you look at the semiconductor, if you look at the resistivity of a semiconductor, it lies approximately between 10 power minus 2 to 10 power 4 ohm meter. Okay, this is the range between which the value of resistivity lies. For whom? For a semiconductor. Now comes an important question. So when we discussed about conductors, that is the third chapter, we would have seen an equation like this. R is equal to R naught into 1 plus alpha into delta T. And rho is equal to rho naught into 1 plus alpha into delta T. Am I right? We would have seen these two equations. But the question is, what is this alpha, guys? Can you tell me what this alpha is all about?
Temperature coefficient.
Very good. It is a temperature coefficient. And is it positive or negative for a conductor?
Positive, sir. For metals, it is positive.
Abdina meaning another, right? If it is positive means what does it mean? It will
increases with increase in temperature, like directly proportional.
Perfect. Very good. So resistivity will increase with temperature. That is what alpha says if it is positive. For whom? For conductors. Whereas semiconductors have a typical kind of behavior. If you see, the resistance of a semiconductor decreases with increase in temperature. Means what can I say about alpha? Alpha in this case will be negative. That is the meaning. Okay, there's a very, very important point to be noted. So can you, they suppose the question is like, let's say it's a 1 mark question. They're saying, name a device which has a negative temperature coefficient. What is it going to be? It's any semiconductor. Okay, you should be able to answer this, right? This behavior is contrary to that of metallic conductor, for which generally the resistance will increase with increase in temperature. When I say metallic, generally metals fall under the group of conductors. So metallic conductors have the resistance increasing with increase in temperature. Okay. So the elements that are classified as semiconductors are silicon, germanium, indium, etc. These are all the elements, but we will be commonly discussing about silicon and germanium alone, because these are the widely available semiconductors, and our discussion is restricted to these two elements. Okay. So moving on to the next concept. When I talk about a semiconductor, when I talk about these three elements, that is conductors, insulators, and semiconductors, what I can speak of is, I can talk about the differentiating factor between these elements, one in terms of resistivity, or the other is in terms of a band called as a valence band or conduction band. Okay, valence band, conduction band, and there is something called as forbidden energy gap that is going to exist between them. Right. So generally, in the first point, if you see, in the introduction part, we have discussed about the difference between the conductor and semiconductors in terms of resistivity. Now we are going to concentrate on discussing the same, that is the difference between these materials in terms of valence band, conduction band, and forbidden energy gap. Guys, shall I proceed? Am I clear till this point? Shall I proceed?
Yes, sir.
Okay. So you would have learned the solid state. I'm not sure if it was, I think it is deleted, right? In your chemistry, solid state is deleted, right? The first chapter
No,
of your
sir,
chemistry.
No,
we
sir, it's there,
studied it.
sir.
It is there, right? But the last part is deleted. The semiconductor part and all those things were not there.
Yes, sir.
Correct? Okay. So when generally when we talk about this germanium and silicon, we talk about the crystal state. That is, you know what is the space center cube, all these things are there, right? Generally crystals, something, a solid which has a definite shape is what we call it as a crystal. We are going to discuss about those materials. So you talk about the atoms of a solid, they are generally arranged in a regular repeated geometric pattern, and the electrons of those electrons in those atoms are obviously going to revolve around the nucleus in certain permitted energy levels according to the Bohr's theory. Right. So here, if you see, the discussion is restricted to solids. Okay. Then, if you talk about the electrons in the inertials, they are strongly bound to the nucleus. This is the known factor, right? So the electrons in the inertials are strongly bound to the nucleus. A band which is occupied by the valence electrons, or a band having the highest energy, is defined as valence band. I need to explain what it is. So we would have heard about bandwidth, right? So what is bandwidth? A certain amount of frequency that is going to exist is what we call it as the bandwidth. Now coming to the same point, see, if you talk about the valence electrons, the electrons are going to have energy associated with them, where they are going to be of slightly greater or lesser value. If you take all those values and put it in a box like this, that is, you take the valence electrons and put it in a box like this, showing that they have different energy levels, then this band is what is called as a valence band. Okay. Now let me come to one point. See, whether you talk about your mobile phone or something. See, for example, you know how a touch screen works, right? So you have a mobile phone. These days, everything is a smartphone. So we are talking about touch screen. This slightly out of your book. So listen to this. Just to share knowledge, I'm discussing. So when I talk about this touch screen, right? What do you generally do? You have an app here. Let's say you have an app which you want to open and see. What do you generally do? You're going to touch it, right? When you touch it, you're able to see that the app is getting opened. Correct? This is a known fact. This is a very simple point. But the question is, what are the backend feature that is running here? How is a device which doesn't have brain able to understand what you're trying to say through your finger? What is actually happening? Can you tell me? Any idea? Okay, I'll put the question in a different way. Is my question clear, guys, to everyone? There is a reason why I'm asking this. I'm trying to connect the dots. Okay.
Sir,
So
operating systems.
Operating system, for sure it is there. Android or iOS, okay.
Yes,
all
sir.
those things are there. Those things are there. That operating system. See, Your operating system is a software. Mithun, try to understand. Okay, software, some code is there. Okay, I accept it. But when you're touching it physically, it's a mechanical process. You don't have any code inside your body, right? How are you able to send that signal? Now you are sending a message. That is why the mobile is able to understand that you are trying to click on this part. How is it able to know?
Some server will be there, sir.
Okay, those things are there, but physically, when you're clicking at a particular location, now think about it. If you take your mobile phone, say there are 100 people who are using this some OTT, okay, some app which is related to OTT. All those 100 people, do you think they will have those particular OTT app at a particular location on the screen? They can keep it anywhere they want, right? Correct?
Yes, sir.
It is the freedom of the user. Wherever you want, you keep it. That's what they say. But my question is, correct, when you're touching that particular coordinate on that particular screen, what do you think is actually happening? If I'll give you a different perspective to it. Let's say you're touching it with the same thing with your bare hands. Yes, you're able to see that the app is getting opened. My question is, do you think the same thing will happen when you touch the screen with the plastic gloves on your finger? Have you ever tried this?
Because it's an insulator, so it won't be able to.
You're able to understand why I'm asking this question.
Yes, sir. We are conductors, so when we touch the screen,
Electricity is conductor, sir.
So you're actually trying to conduct it.
Low voltage electricity.
Yes, you're creating a voltage. Actually, what will happen is there will be microprocessors in the back end. Those microprocessors will receive a signal whenever there is an electrical conductivity taking place at that particular coordinate. That is why it is able to open that app. See, for example, you click on Netflix, Prime is not getting open. So that's how it works. It is able to have that accuracy and precision only because you're creating a small amount of electrical circuit at the instant you touch the screen. Okay. I ask this question is, the main purpose of any semiconductor device is to enable conductivity, correct? So if it has to enable conductivity, if I have to say any material is able to conduct, then what do I need to have is the immediate question I need to ask. What do I need to have? I'll give you a hint because I want the answers from your mouth. I can say, but I want you to think. If I take a conductor, generally inside a conductor, what is present?
electrons.
Free electrons.
Free electrons.
They're not electrons, they're free electrons. Somebody told free electrons, it is right. So what do I mean by free electrons?
They'll be like they can move from one point to another when electricity is
from
applied.
one point to perfect. So what is happening if I talk about a material? Any material in this world is made up of atoms, and every atom contains electrons. These electrons are bound to the nucleus due to the electrostatic attraction. If I'm able to release those electrons from which shell? If I'm able to release that electron from the valence shell, they get free from that particular electrostatic bonding, due to which they are able to participate in conducting. They're able to understand. So free electrons is the precise word which we use. So from the idea of conductivity, I'm able to understand that electrons have an important role here. So when generally we think of an electrons from the basics of atoms and nuclei, we are able to understand that electrons in the valence shell are the ones which can participate more. That is why when you see conductors, they will have a valency less than 4. Correct? So when you talk about those metals, they have valency less than 4, due to which it is easy for us to remove those electrons from the valence shell, so that they have different kind of energy, due to which they are able to participate in conducting. And those kind of electrons are called as conducting electrons, and the band to which they belong is what is called as conduction band. So you're able to understand the whole story. What I'm trying to say is, if you want, this is a logic you need to think of. The right question to ask if you want to make some material to start conducting is, you need to ensure that energy is supplied to those electrons in which shell? In the valence shell, so that they start moving into the next level and become conducting. Okay, so the valence band may be partially or completely filled. This band can never be empty. This is one of the points. I'll come to that point. Listen to this. In some materials, the valence electrons are loosely attached to the nucleus, due to which even at room temperature, some of the valence electrons can leave the valence band. Then those kind of electrons are what are called as free electrons, not the ones which are inside the atom. They are the ones which are contributing in the outermost orbit. Okay. And these are the electrons which are responsible for the conduction of current in a conductor and henceforth called as the conduction electrons. So if you are able to draw the energy band, means these electrons will definitely have energy. If you are able to take energy values and put them in a small rectangular space, that is, you are able to give a small area to it, then that kind of a band is what is called as conduction band. So what is the whole moral of the story? If you want any particular device, I'm not talking about a conductor, insulator, or semiconductor. Any device or any material in this world can conduct only if the electrons in the valence band are able to jump into the conduction band. Is my point clear? Is my point clear? Guys, is it clear or not? Can you have a confirmation?
Yes,
yeah. Okay. So if you talk about a conduction band, the conduction band can be empty or partially filled. But when we talk about a valence band can never be empty. That is the first point you need to make a note of. Okay, I want to highlight this thing. Valence band can never be empty, whereas a conduction band can be empty or partially filled band also. Okay.
Sir, what is conduction band, sir?
Conduction band na the valence electrons are clear. Valence electrons are bound to the nucleus. So if you recollect from the atoms chapter, we derived something called as energy of an electron in n minus 13.6 into something z square divided by n square electron volt. But you remember something like this we have derived? So energy of the electron in the nth orbit, right?
Yes,
so all the electrons in the valence shell will also have some energy associated with it. If you take all those electrons, if you take the energy of all those electrons and put it in a graphical representation, then they don't fall on a straight line, rather they fall in a small area called as the valence band. Now, what did I say? If you give energy to it, then these valence electron will exhibit the tendency of escaping from the electrostatic pull and they become free. Now, what are these electrons called as? These are called as electron which has escaped. Generally, we call them as free electrons. Okay. If these free electrons are able to participate in the conduction process, now tell me one logic. Okay. Does valence electron have more amount of energy or the conduction electron have more amount of energy?
Conduction band, sir.
It is conduction because valence electron is restricted. When you have restriction, then your energy levels are going to be low, right? So when something is free, you will definitely be at a higher energy. Mithun, to answer your question, if the valence electrons become free electrons, they have more amount of energy, right? If you take all those electrons and you calculate their energy and put it in a box, okay, you put it in a box, then that box is what is called as conduction band. So if I have to explain you in terms of energy band diagram, then if the electrons in the valence shell are here in the valence band, then if you need to send them to a higher energy level, which I call it as conduction band, then we need to supply some energy. The amount of energy that we need to supply for the electrons to jump from valence to conduction band is what is called as forbidden energy gap.
Sir, can I see the
Means what-
definition for conduction band again, sir?
You want me to say or you want to see here?
Sir, can you
They
say?
they are response. So, did you understand till this point? Free electrons very important.
Yes, sir.
They are the ones. These free electrons are the ones which are responsible for conduction of current in a conductor. Hence, they can also be called as conduction electrons. So, these conduction electrons will have energy down. That's visualize the energy I can't show it. Right? They have some energy. Means they have a number associated with them in terms of energy. If you take that energy and put it, see, it doesn't mean I'm taking the electrons and putting them. Okay. If I take all the energy values of those electrons and I try to plot a graph, then I will not get a straight line like this. Means all the free electrons will not have the same amount of energy. They will have a varying amount of energy, which will be of slighter difference. There is a small region that we are giving to it. then that region where all these conduction electrons can participate is what is called as conduction band. There is no proper definition for it. You talk about the band now, rectangle, small rectangle kind of thing is what we call it as a band. The band occupied by these electrons, which electrons? By the conduction electrons is what we call it as conduction. I'm not sure if you understood. Just give me a confirmation.
Understood, sir.
Understood, right? Okay. So then what we do, the separation. Tell me.
Sir, if conduction band is empty, then how it can conduct electricity, sir?
It need not know. If the conduction band is empty, it's an insulator. That's why I told you this concept is not restricted to metals alone. Yeah. So separation between the valence band and the conduction band is generally known as the forbidden energy gap. Okay. So if you have an electron which is to be transferred from valence band to a conduction band, then obviously what do we need to do? We need to supply energy externally, which is equal to the forbidden energy gap. I hope I answered this question. So this is called as the energy band diagram, where energy level in terms of electron volt is restricted to y-axis, and x-axis is nothing actually. It's only about this thing, because we are concerned about how much energy we need to supply so that that material becomes a conducting material. Okay. So if I take the same energy band diagram and apply it to all the three devices, if I take an insulator, okay, in an insulator, even before I show you, right, you guys guess, is it easy for you to push an electron from the valence band to the conduction band, or is it tough with respect to an insulator?
Tough, sir.
Tough,
it
sir.
is tough, right? Then what can I say? Can I say that the forbidden energy gap is more? Right? So that's how the statement starts. In an insulator, the forbidden energy gap is very large. In general, the forbidden energy gap is generally more than 3 electron volt, and almost no electrons are available for conduction. That is why I told you conduction band can be empty also. Therefore, what we need to do is we need to supply large amount of energy to valence electron to enable it to move to the conduction band. So generally, if you take the materials like glass, the valence band is completely filled at 0 Kelvin. Okay, so that's what happens with respect to an insulator. Second is the energy gap between a valence band and conduction band in the case of an insulator is generally of the order of 10 electron volt. Imagine 10 electron volt is what we need to supply. Then what happens even in the presence of high electric field? Generally, why we use the word high electric field is because electric field has the property of emitting an electron from the metal surface. Like, see, for example, if I have a valence electron, in photoelectric effect, what did we learn? If you make a light of energy h nu fall on the valence electron, then the valence electron will jump and it will acquire some kinetic energy. So that is why I'm using photons. That is why I called it as photoelectric effect. In a similar way, instead of using photons, if I use electric field, then I will call it as field emission. Okay. So what they are trying to say here is, even in the presence of high electric field, the electrons cannot move from valence band to conduction band in the case of an insulator. So if the electron is supplied with high energy, it can jump across the forbidden gap. Means even if you supply high energy, from here, if you need to push it here, it is a tough job. Rather, you can push it to some intermediate level between the valence and the conduction band, obviously, which is of no use for us. That is the reason why we don't use insulators at all in the case of conduction, because you cannot make it conduct. When it is so resistive, what are we going to do? Nothing. Right? Similarly, when you increase the temperature, then there is possibility some electrons will move to the conduction band. Right? So this is the reason why certain materials which are insulators at room temperature become conductors at higher temperature. But if you see in real time, if you're using a mobile phone, right, like I told you about the example of conduction, and you're trying to say that conduction is possible only at higher temperature, means your mobile needs to be on a fire, right? It needs to be put on a stove and then you need to use it, which is not a practical thing, right? That is why we don't take the concept of insulators in this kind of a process at all. The resistivity of insulator approximately lies between 10 power 11 to 10 power 16 ohm meter, which is very, very, very high value. Okay. Similarly, if you talk about the semiconductors, which we are going to concentrate upon, what do you think is going to happen here? In the case of semiconductor, the forbidden gap is very small generally. Okay. So if you talk about germanium and silicon, they are the best examples of semiconductors. And if you talk about the forbidden energy gap, they are generally of the order of 0.7 electron volt for germanium and 1.1 electron volt for silicon. And what happens? There are generally no electrons in the conduction band. The valence band is completely filled at 0 Kelvin. Okay, that is absolute zero temperature. When you supply a small amount of energy also, the electrons can jump from the valence band to the conduction band. Okay. For example, if the temperature is raised, the forbidden gap is decreased and some electrons are liberated into the conduction band. So the conductivity of a semiconductor is generally of the order of 10 power 2 mho per meter inverse. Here I'm talking about conductivity, not resistivity. So it is 100 ohm inverse per meter inverse. Okay, the first thing that is to be known is understanding the energy band diagram for the different kinds of devices. Obviously, when you talk about a conductor, what will happen? It is going to be very, very small. So, having said this, observe, if I talk about the energy band diagram for a conductor, what is happening? The valence band and the conduction band are almost overlapping on each other, that there is no band gap at all that is existing. Whereas when you talk about a semiconductor, what is happening? There is a narrow band gap that is going to exist, which is all of the order of 0.7 to 1.1 electron volt, depending on what kind of a material you're using, whether you're using germanium or silicon. Whereas when you talk about an insulator, the energy band gap is approximately plus 5 electron volt or more than that. Generally, how we saw. For a glass, it is around 10 electron volt, right? Which is a very, very high value. Are you able to understand this point, guys?
Yes, sir.
So valence band, conduction band, and forbidden energy gap for all these three devices. Now, since our chapter is related to semiconductors, we'll discuss about semiconductors. So basically in semiconductors, there are two types of charge carriers that you have. So when you talk about a conductor, inside a conductor, you have only free electrons. Whereas when you talk about a semiconductor, right, you have electrons and holes, both of which are existing. Okay. So basically, I need to explain one more thing. When you talk about a semiconductor, basically semiconductors are classified into two types. One is called as intrinsic and the second is called as extrinsic. Okay. So generally when I say intrinsic, it is a pure form, and extrinsic is it is the impure form. Okay. Now listen to this. When you talk about the electrons in intrinsic semiconductor, as of now, remember, pure semiconductor is what is intrinsic. Pure means, let's say you get a germanium in your hand directly from, you get it naturally from the atmosphere itself, okay, from our nature, then that kind of a semiconductor is what is called as intrinsic semiconductor. Okay. The electrons in the intrinsic semiconductor which move into the conduction band at higher temperature are called as intrinsic carriers. So generally when you talk about an intrinsic semiconductor, right, the first point to be noted is in natural form, semiconductors are not very good conductors of electricity. So you have to do some changes to its natural form to make it conductive, about which we will discuss later. Now I am concentrating only on the concept of electrons and holes. Okay. So if you talk about the valence band, in the valence band, a vacancy is created at the place where electron was present. Okay. So what is happening? Listen to this carefully. The electrons in intrinsic semiconductor, if they move to the conduction band at high temperature, then what will happen? It looks something like this. There is the valence band, there is the conduction band. Let's say there are electrons which are jumps from the valence band to the conduction band. Then what can I say? I can say that these parts where the electron has come out of the valence band has created a vacancy. Okay. And that vacancy is what is called as a hole technically. A hole in the case of a semiconductor is basically a virtual positive charge. It is a virtual positive charge. Have that in your mind. So in the valence band, a vacancy is created at a place where electron was present before it had moved into the conduction band. And this vacancy is what we call it as hole. So generally, when you talk about a semiconductor, there are two things. One is electron and the second is hole, right? So for that, we will try to understand with the help of a crystal diagram. See. So when I talk about germanium, the valence electrons are 4. So when you talk about germanium, the number of valence electrons in it is 4. When the valence electrons are 4, then what kind of a bond does it form? It forms a covalent bond by sharing the electron with the neighboring germanium atoms. So it has the four electrons in the outer or valence orbit. These electrons are known as valence electrons. When two atoms of germanium are brought close to each other, then you will have a covalent bond which is formed between the atoms. Right. Now the question is, if you are able to supply some additional energy, then what can happen is one of the electrons which has participated in the bond can leave. Okay, it can leave and it is now free to move inside the crystal lattice. It is now free to move inside the crystal lattice. So this is a free electron. Then there is a vacancy of electron which has got created at this place. What is it called as? That vacancy is what we call it as a hole. Okay, that vacancy is what I call it as a hole. While coming out of the bond, a hole is to be created at its place, which is usually represented by an open circle. So if you put a dotted circle like this, that is an electron. If you put an open circle like this, that is a hole. And what happens is an electron from the neighboring atom. Think of it. You have an electron in the neighboring atom. The electron from the neighboring atom can break the bond and it will try to come and fill this. Then what is happening? Then there is a hole created in this bond. Similarly, the electron from here will come and form here. There is a hole created at this place. As a result of which, what is happening is, it is appearing as if the hole is moving from one place to another. But actually, who is moving? It is the electrons, right? By the electrons trying to fill the gaps that are created by holes, it is appearing as if the holes are traveling from one place to another. And this type of a current is what we call it as hole current. Now you read and see, you'll understand. An electron from the neighboring atom can break the covalent bond and can occupy this hole, creating a hole at another place. Since an electron has negative unit charge, the hole is associated with unit positive charge. The importance of the hole is that it may serve as a carrier of electricity in the same manner as that of the free electrons, but in opposite direction. We know that free electrons move from lower to higher potential, whereas protons, that is positive charges, move from higher to lower potential, right? So hole serves the purpose of a positive charge in the case of conductors. Is it clear? Guys, can I have a confirmation? Is it clear?
Yes.
Yes, sir.
Okay. Now we are going to talk about the different types of semiconductors. One is called as intrinsic, which is also called as pure semiconductor, and the second is called as extrinsic. So when I talk about an intrinsic semiconductor, it is pure and obviously it doesn't contain any impurity. So if you talk about a semiconductor which is pure and contains no impurity, then you call that particular semiconductor as an intrinsic semiconductor. Okay, one important point to be noted is in an intrinsic semiconductor, if you have the number of electrons, so the number of electrons is equal to the number of holes, right? So the common examples of intrinsic semiconductors are basically pure germanium and silicon. Now the next question is, the forbidden energy gap is there, right? In the case of a semiconductor, we know this fact. The forbidden energy gap is so small that even at ordinary temperature, there are many electrons which possess sufficient energy to cross the forbidden energy gap and they enter into the conduction band. So when is it happening? Even at ordinary room temperature, this can happen. So you can ask me a question, sir, at room temperature itself, the valence electrons are able to jump into the conduction band. So you're trying to say that intrinsic semiconductors are good conductors of electricity? No, they are not. Okay. So they are generally not good conductors of electricity. This is going to get saturated at some point. This is a natural process which is happening. This is going to get saturated at some point. Now, what we need to do is, even if I don't have room temperature, I want my mobile phone to work even in an AC. If that should happen, then I need to ensure that the conduction is happening under any temperature circumstance. For that, what we will do is, we will try to convert an intrinsic semiconductor into another type, that is the opposite part, which is called as the extrinsic semiconductor, for which we are going to follow a process called as doping a semiconductor. So what is doping is, if you talk about electrons and holes can be generated in a semiconductor crystal with heat energy or light energy. But in these cases, if you observe, conductivity remains low. So what they are trying to say is, semiconductor crystal, even in the intrinsic form, is not going to be a very great conductor of electricity. So how do I make it efficient? The efficient and the convenient method of generating free electrons and holes is by doing something like this. Is by adding small amount of selected impurity inside the crystal. So this is the important step that we need to follow. And this kind of a process of you adding impurity to the existing, impurity to an intrinsic semiconductor is what is called as doping a semiconductor. Okay. And generally, when you add this impurity, the impurity that is to be added is of the order of 100 parts per million. It is very, very small. Okay. And this is the important thing. The process of addition of very small amount of impurity to an intrinsic semiconductor is what we call it as doping. And the impurity atoms are generally called as dopants. Okay. The impurity atom which you are adding is what is called as dopants. And the semiconductor containing the impurity atoms is known as impure or doped or extrinsic semiconductor. Is it clear till this step?
Yes, sir.
Right. Now you can ask me a question. What are all the methods that are used to dope a semiconductor? First is, you take the impurity atoms. Impurity are generally pentavalent or trivalent impurities. If you take the impurity atoms, they are added to the semiconductor in its molten state. You take a semiconductor, melt it, convert it to molten state, and then start adding the impurity. That is one of the ways. Second is, the pure semiconductor is bombarded by ions of impurity atoms. So if you take this pure semiconductor, then you bombard it with the impurity ions, the ions of impurity atoms. Then also you can make it an extrinsic semiconductor. And the third one is, when the semiconductor crystal containing the impurity atoms is heated, the impurity atoms diffuse into the hot crystal. So when you take a semiconductor crystal containing the impurity atom and you start heating it, then the impurities will start getting diffused into the hot crystal. And usually, if you take the doping material, it is either a pentavalent atom like bismuth, antimony, phosphorus, arsenic, etc., which have 5 valence electrons, or you take trivalent atoms, which are aluminum, gallium, indium, boron, which have only 3 valence electrons. Now, I have an important question to ask. Why are we choosing pentavalent or trivalent? Where did we get this idea? So the logic is very simple. When you talk about the semiconductor, what are the two devices that come to your mind? Two elements that come to your mind: germanium and
Silicon, germanium.
silicon, germanium. If you talk about those materials, how many electrons do they have in the valence shell?
4.
So 4 means they can form covalent bond. So if you talk about pentavalent, it is 1 more than that 4, and trivalent, it is 1 less than that 4. So what will happen by you adding this pentavalent impurity is, 1 minute. What happens when you add this pentavalent impurity is, the pentavalent doping atom is known as the donor atom since it donates 1 electron to the conduction band of the pure semiconductor. So this is the thing you need to remember. The pentavalent doping atom is also known as the donor atom because it is donating 1 electron. So as I asked you from the beginning, the only objective of reading about all these devices is to increase the conducting property of that particular material. So if I have to increase the conducting property of that particular material, I need to have free charge carriers. So what do I need to have? I need to have free charge carriers. Those free charge carriers can either be electrons or holes. So the question is, how do I generate excess amount of electrons? Is by adding an impurity which has one number more than that 4. So that from the pentavalent, 4 electrons will participate in the covalent bonding and 1 electron will be free. Similarly, when you talk about a trivalent impurity, the trivalent atom is generally called as an acceptor atom because it has a tendency to accept electrons from the pure semiconductor atom. Now, why we are choosing trivalent is because we know that for a covalent bond to be formed, 4 electrons are to be there. So if there is there are 4 germanium atoms surrounding the impurity atom, then what will happen is the impurity has 3 electrons and germanium has 4 electrons. 3 electrons from germanium will participate in the bonding and 1 electron will be left out, for which I will show you how it actually looks. Okay. So when I talk about an extrinsic semiconductor, listen, an extrinsic semiconductor is one in which an impurity with valency higher or lower than the valency of the pure semiconductor is added. So to increase the electrical conductivity, so as to increase the electrical conductivity of that semiconductor. So depending on the type of impurity atoms that are added, an intrinsic semiconductor is basically classified into 2 types, which is called as the N-type and P-type. You can either say N-type or P-type. Now you will understand why we are talking about this pentavalent. Listen to this. If I talk about an N-type semiconductor, okay, when you add small amount of pentavalent impurity such as arsenic to a pure germanium semiconductor crystal, then that crystal which is getting, then the crystal that is getting generated is what is called as an N-type semiconductor. Okay, so let's understand. I have arsenic here. Okay, and this arsenic is added to the pure germanium atom. So we know that germanium has 4 valence electrons. 4 valence electrons. This one is from germanium, this one is from germanium, this one, and this one is from germanium. And arsenic has 5. So 1, 2, 3, 4. 4 electrons have participated in the covalent bond, and 1 electron is left free. And that electron is what is going to participate in the conduction of that particular semiconductor, which we call it as free electron. Now, did you understand why we are adding?
One electron moves to the conduction band. Is it due to the repulsive force through that it gains energy? Or
Not because of repulsive force. It is not because of repulsive force. It is purely because it didn't participate in the bonding at all.
so how does it get that energy to move? Or
It is free electron already, right? So it is not a valence electron. These are valence electrons. And this, okay, it didn't participate means there is nothing to hold it. So try to understand, if nobody is going to hold you, you're directly at which level? You're at the conduction level. But you asked a very good question. Your question is this electron directly going to be in the conduction band? Is that what you're asking?
yes, sir.
It is actually not going to be in the conduction band, but it will be closer to the conduction band. I'm happy with your question, actually. It's a good thought process. So it's a very good question, guys. What she is asking is, does this free electron get the energy naturally so that it can directly go and fall into the conduction band? No. But what we are going to do is, instead of pushing an electron from valence band to conduction band, this particular free electron will have an energy which is closer to the conduction band. That is, listen to this. So figure below shows the crystal structure obtained when pentavalent arsenic impurity is added with pure germanium crystal. So just give me a confirmation. Is this diagram clear? It's simple chemistry, right? Right, which you people are better than me. So did you understand?
Yes.
Right. Next. So I the same story. The 4 valence electrons of arsenic atom form covalent bonds with the electrons of neighboring 4 germanium. The 5th electron is loosely bound. Now concentrate. This electron can move about almost as freely as an electron in a conductor, and hence, in the case of an N-type semiconductor, who will participate in the majority conduction? It is the electrons that will participate. Now comes an important question. If I have to draw an energy band diagram for an N-type semiconductor, I have valence band and conduction band. That there is an intermediate level that is existing between these two, which we call it as the donor level. Means you spoke about the free electron, right? The free electron will neither be in the valence band nor in the conduction band, but rather it is going to be here. This is the amount of energy it has. So think of it logically. If I have to send an electron from valence band to conduction band, I need to supply, let's say, energy X. If I have to send an electron from donor level to conduction band, I need to supply energy Y. Which one is lower?
Why?
Obviously Y, right? So from this, is it not clear that by you adding the impurities, you have cut down the concept of this the electron jumping from valence band to energy band, and you have also tried to reduce the forbidden energy gap, due to which achieving conduction even at room temperature becomes an easy process. Is the point clear?
Yes, sir.
Right. So that is why we are doing all these things. Okay. So in the energy band picture, I need to explain about this donor level. In the energy band picture, the energy state corresponding to the 5th valence electron is in the forbidden gap and lies slightly below the conduction band. And that level is what we call it as the donor level. So the 5th electron is transferred to the conduction band. The arsenic atom becomes positively charged immobile ion. So when this electron jumps into where? When this electron jumps into the conduction band, then the arsenic part is there. No, it will become an ion. Because till now, where was that electron? It was still inside the crystal lattice only. Right now, it has become an ion, which becomes a non. So it becomes an immobile ion, which is not going to participate. Then this electron will take care of the conduction. Okay. Then what will happen? Like this, one arsenic is able to release one free electron. So we have mentioned the concentration level. It is around 100 parts per million. So 100 parts added per 1 million is 10 lakhs, that is 10 power 6. So that is a small amount of impurity that is enough to create conduction. Okay. So each impurity atom donates one free electron to the semiconductor, and these impurity atoms are what are called as donors. So in this case, arsenic is called as a donor. Right? Because it is donating an electron. So if I have to talk about an N-type semiconductor, can I say the number of electrons are going to be greater than the number of holes? Right. Clear? So what we can say, what we can say in an N-type semiconductor, there is another important point you need to make a note of. Free electrons are the majority charge carriers and holes are the minority charge carriers. This is what happens. Next is, if I talk about a P-type semiconductor, okay. So even before I show you, you guys think and tell me what will happen. When you add a trivalent impurity, let's say we are adding boron, then what will happen? 3 electrons from the boron will get combined with 3 neighboring germanium atoms, and the 4th germanium atom will not have an electron to complete the bond, as a result of which there is a vacancy that will exist, something like this. Right, there is something like this that is going to exist. Is it clear? Now, if I draw an energy band diagram for this, okay. So what is boron called as? If arsenic is called as a donor atom, then what is boron called as?
Acceptor atom.
It's called as an acceptor atom. So if the free electron is able to be in a place called as a donor level, where do you think this hole will be present? So what is the counterpart of donor level?
Acceptor
going
level.
Acceptor level. So where is that acceptor level going to be there? It will be closer to the valence band.
Sir, but hole will be present only in the valence band, right? Like how can it be higher than the valence band?
Which one?
This acceptor level, sir,
Okay.
it's going to be the hole that is present, or
But I'm saying here, listen again. Though it is hole, what is going to happen is, when I explained about hole current, did you understand how the hole is actually moving?
yes, sir.
So when hole is moving, then what is going to happen? Like hole is actually moving due to the movement of holes, or is it because of the movement of electrons?
Electrons.
So that is what we are trying to talk about. So when you talk about the valence band, you're going to have only electrons. So let me read that point. Maybe you'll understand. See, this is clear, right? The 3 valence electrons of the boron atom form the covalent bonds with valence electrons from 3 neighboring germanium atom. The fourth one has only 1 valence electron which is available for germanium atom, and there is a deficiency of 1 electron which is called as holes. Right? Hence, for each boron atom added, you can create 1 hole. Since the holes can accept electrons from the neighborhood, this impurity is called as acceptor. Now see this point. The hole may be filled by the electron from the neighboring atom. This is what I've been saying from the beginning. Okay, creating a hole in that position from where the electron moves, and this process continues, and the hole starts moving in a random manner due to thermal effects. And this kind of a current is called as hole current. Okay. Since the hole is associated with the positive charge moving from one position to another, there is a type of semiconductor which is called as P-type semiconductor. So for a P-type semiconductor, the acceptor impurity produces an energy level just above the valence band as shown in the figure. Right? Since the now you will get the point. See, since the energy difference between the acceptor energy level and the valence band is much smaller, electrons from the valence band can easily jump into the acceptor level by thermal agitation. So what is going to happen here is, since there is a vacancy, the valence electrons are there, right? Right?
Yes,
what will
sir.
happen to this? What will happen to this valence electrons? The valence electrons can easily jump into this acceptor level because there is a deficiency of electrons. It is because these electrons are only moving. No. So if it is able to jump it here, then what are you again trying to do with respect to the forbidden energy gap? You're
Reduce
again
it.
reduce it. So what is going to happen? The holes will be present. So you got your answer now, right? Where will the holes be present?
In the valence bond only.
In the valence band only. It is the electrons which are actually jumping to the acceptor level, and from there they will jump into the conduction band. Got it?
Yes, sir.
Right. Okay. So this is all about an extrinsic and the 2 types of semiconductors, which are the P-type and the N-type. And tomorrow we will discuss about an important type of diode, which is called as the PN junction diode. If possible, I'll complete it by tomorrow itself. If not, maybe we'll take 1 more class. That's it. Not a big deal. Is that clear? So
Yes, sir.
that's from my side, guys. You can wind up.
Thank you, sir.
Thank you.
Thank you, sir.